Hi, for those of you that don't know me, but I guess I'm Bruno, and I'm gonna be telling you basically what I've been doing for the past year of my first year of PhD, well, here at MSP in Glasgow, and that is I've been thinking about generalized open learners. It's learning algorithms in general, but those specifically based on artificial neural networks. And there in brackets it says agents because it's sort of a bit more general than actual just neural networks. But we're gonna see what this is about. And I mean, this is also done jointly with a bunch of people with MSP. I've been talking with anybody who's really interested in this, and also with Geoffrey Krathfeld, Paul Wilson, Fabio Zanassi, and some other people. So yeah, I'm just gonna start. So what am I gonna be talking about is how to understand the information flow in artificial neural networks. Of course, using some abstract machinery. So what's the idea? Why am I doing all of this? Well, I think it's just a first step, concrete proxy for understanding some more general cybernetic systems. So hopefully all the things we do here will transfer to some more funky systems, systems with agency or something like this. And how? What's the main idea? It's to take parameterization and bidirectionality seriously. So what do I exactly mean by this? So this is something that's related really tightly with open games, and open games are an inspiration and influence in this work. And it's also related to all these things happening with backpropos functor, which is another paper, recently published paper, which did a first step of applying category theory to machine learning. So it's quite interesting to first just look at the rough outline of information flow in these systems. So in both learners and open games, we have a thing here, a box that has multiple inputs and outputs, multiple ports. And it's bidirectional, which means that we think of it as things flowing on top, and then there's some things flowing backwards. So both of them take some inputs, such as things that we want to predict, like data points, or states, as it's called in open games, and give out some outputs or some moves that a player makes. They both, after these moves or outputs are done, they receive some feedback about how they were doing in forms of gradients, derivatives, or in open games, this is called utility. And since we want to consider learners and games composed in sequence, they pass back this error signal, which also gradients, to previous learners or games, or they pass back co-utility. But what's interesting here is that in addition to this forward-backward interaction, there is something happening behind the scenes. In open games, we have, namely, we have strategies, which, and I'm drawing them as an input here. We have strategies which influence these things and actually give us a lens, while in learning, we have things that we call parameters. So it's interesting to see all these similarities. And actually, the information flow between learners and open games is so similar that I'm using both as inspiration for each other and trying to find a really nice perspective on all of this. But what's the most interesting thing is that there is a perhaps surprising way to see this. Just as we have inputs and outputs on the left and the right side for parameters or strategies which I'm drawing on top, for learners, we know we have a thing called, also parameters. So we compute the updated parameter. So there's a thing coming out, which is sort of opposite of the parameters that are coming in. And in open games, it's quite interesting now, because in open games, we have a thing called equilibrium predicate or best response, but it's not exactly of the same vein as parameters. So I'm going to write it here while knowing it's almost there. So the rough idea is now to see that here we have two notions at play. One of them is parameterization, and the other one is bidirectionality. So what I mean by this is that there's things flowing on the right and they're parameterized somehow, and I'm being intentionally vague. And there is an idea that we can just have things flowing backwards and forwards. So the how of this talk is going to be to take these notions seriously, to define them separately using abstract nonsense of category theory, and then compose them and see what we get. And we're going to get something a bit non-trivial. And I'm calling these generalized open learners, but they're quite similar to open games. And maybe you can call them agents. So it's really you have to figure out what's the best perspective on this. So yeah, that's the main idea. So results, there's a bunch of things that's happened. In this, we've so far generalized the category learn from backpurpose functor into these generalized open learners, which actually simplifies a bunch of complex proofs and structures. It turns out the optimizers in machine learning, such as gradient descent, momentum, Adam, and all these things, those are actually lenses. So that's a pretty interesting thing for me. And it turns out also in backpurpose functor, the definition of two cells is you could say wrong, but and I will say that right now because we fixed it. And now when you think about two cells, it turns out two cells in the category of generalized open learners will be actually lenses. So two cells are lenses or optics. It won't really matter for me right now. That's not what I'm focusing on, which actually means that optimizers will be the two cells. So there's quite a few interesting ways to think about it. And what also we've done is just integrated all this stuff with work done on reverse differential categories. So we can talk about learning on arbitrary reverse differential categories as opposed to just smooth. Another example that came out after actually we did this was the work on learning on Boolean circuits. So the game plan will be roughly to first talk about parametrization, define this abstractly, and then apply it to, I'm going to talk about bidirectionality, which is going to be optics lenses, and I'm going to briefly mention it. And the idea would be to apply it and to get something that uses both. And we're going to see there's something non-trivial coming out. I'm going to talk about differentiation, or how do we construct these learners, and basically, how does this learning work? What's the parameter update? And I'm going to give some examples here. Is there a question about the game plan before I start? Okay, I guess not. Feel free to ask. So I'm going to start with parametrization, and what we're going to fix right now is a symmetric monodal category. So we can put things in sequence and we can put things in parallel. Oh, I see there's two things in the chat now.
It's just me writing down some thoughts so I don't forget.
Okay, yeah. So parametrization. I'm going to define a category right now. So I'm going to fix a symmetric model category C, and then define a category, actually a two category called para C. This is going to be our canonical notion. So the idea is to really put all the idea about two cells and parameterization here, and then just to apply this to, we should keep in mind that C is going to be replaced by optics C at one point, and I'm going to talk about it. But for now, para C is a category which objects, it shares them with C. So objects in para are objects of C. And the set of morphisms between any two objects in para is basically this. You can think of this as a category of elements, or as just the sum of all P's. So what's a morphism between A and B? Well, you first choose an object P in the category C, and you choose a map F, which goes from P times A into B. So a morphism from A to B is a parametrized morphism. And you can choose what P you want. And interestingly enough, we also have a notion of a two cell. So in this two category, a two cell is a reparametrization. So a two cell, we have an object A and B, and if you have two maps, one, it's a P parametrized map F, and the other one is a Q parametrized map G, a two cell between these parametrized maps is a map in C R, which reparametrizes from Q into P. such that a particular diagram commutes. So what does that mean? If you start from, and you note that this goes the opposite way. So it goes from Q to P, but here we have from P to Q. So what does that mean is that if you start from Q times A and use G to get a B, well, that should be the same as reparametrizing and then using the F. So there's a few examples of this, and it's all the canonical ones where the monodal product is given by the Cartesian product. So you can think of para set, where objects are sets and your functions are parametrized functions. You can think of para smooth, which is where objects are Euclidean spaces and your maps aren't smooth maps, they're parametrized smooth maps. Interestingly enough, this category para smooth is isomorphic to category called just para in backpropas functor. So this is, as far as I know, where this idea originated, and it's been generalized a few times, and I'm just restating this definition now, but I understand to be the most general setting. But it started in the backpropas functor specified on smooth spaces. And we're going to be talking about para-optic C later. So what's interesting about this is that I'm going to be using a particular graphical language, and I'm going to quickly just say how I think of it. When I tell you I have a parametrized map P times A to B, in string diagrams, you would draw it like this, with 2 inputs and 1 output. However, in machine learning, and it turns out in open games, strategies have they're on a different cast, right? They're in a different world, or you could argue they're in a different world altogether. And it seems reasonable to draw them coming from the top. Turns out this actually simplifies quite a bit of things. When you compose 2 maps, for instance, if the types match, you just put them like this. And of course, the parameter space of the composite is just the tensor, starts from A to C, and the tensor is the tensor of the parameter space. So it simplifies, at least visually, what's happening. But also, your usual 2 cells, which I told you it's a map R such that something works. Well, your 2 cells are now just becoming vertical reparameterizations. So your Q map would be something that's the big box. And I'm not going to talk too much about it, but just say that it's grounded in the language of double categories. So you could, when I draw this map, you could think of a bottom actually being the monodal unit that comes out. And there's all this work being done on this, but it's not the focus in the talk so far. So this para is actually symmetric monodal. So para C is a symmetric monodal category. That's quite important, and it's going to have a bunch of other nuts properties. So if I have a parametrized map, and let's say this one goes from A to B with parameters F, and this one goes from C to D with parameters Q. Well, I can tensor both of these, and I can imagine them as a big parametrized map. There's a big parametrized map which goes from A tensor C, it goes to B tensor D, and it has parameters P tensor Q. And you can show this is all coherent and well-defined. It's also interesting that para is natural with respect to base change. So, we defined para C as a symmetric monodal category, but if I have a functor from C to D, then it turns out that also there's a functor from para C to para D. So what does that mean? How is this functor defined? Well, it's called para F, obviously. So if I'm in para C, it's going to map an object A to whatever F maps it to. So it's going to be mapped to FA, and B is going to be mapped to FB. Now, interestingly enough, parameters, I have to map a morphism, which goes from P to F. Which is a P parameterized morphism F. It will be mapped to something. Well, we know P gets mapped to FP, but the question is, what is the morphism? So we have to provide a morphism F prime here. I'm calling it F prime. And the idea is, well, we know it goes from parameters times the input to the output. So it goes from FP tensor FA to FB. We obviously can use F we can obviously apply the big functor f into big functor f to the small f, but we're going to get something that goes from fb tensor a into fb. And to do the final connection, we just use the laxator of the monodal product, of the monodal functor, since f is a symmetric monodal functor. So why am I telling you this? I'm sort of defining everything beforehand, and this is going to be especially relevant to neural networks. We're going to have a morphism from para C to para optic C, and it's going to be given by just the functor para, and it's not really related, with neural networks. So, and it turns out para, I've given you how it acts in monodal categories. I've given you how it acts in monodal functors. It's also an endofunctor on symmetric monodal categories. It's a monad. There is a lot more structure. You can think of it using the Grothendieck construction. It's a co-Kleisli category of graded co-monad. There is all these interesting perspectives, but I'm not going to talk too much about that. What I'm going to do now is first tell you what optics briefly are, and then tell you how we can apply it to optics. But before that, is there any question about this so far?
I have a question.
Yeah.
You mentioned briefly all those cute relationships or constructions for para. Is there somewhere I can read about that?
Yeah, interestingly
There's various different perspectives. Yeah.
Interestingly enough, you're the nth person asking me about this. No, there should be really some. I think at the moment you can read about it somewhere on Zulip in a thread where I wrote a bit about it. But basically, no. I should write about it somewhere. Yeah.
Because that's just. I mean, you just listed a whole bunch of things, and I don't know. I mean, I guess I could think about it a bit myself, but I would like to see it.
It's something I actually been meaning to maybe write and put up somewhere, all these various categorical ways of thinking about it. But the unfortunate answer right now is no, you can't.
Okay, cool. Well, I look forward to seeing a note on that.
Yeah. Okay, so let's move on. Let's move to bidirectionality. And why am I calling this bidirectionality instead of perhaps lenses, optics, or dependent lenses? Is because at the moment, I don't really care which of these particular frameworks we're using. I'm going to be focusing on optics as the canonical, quote unquote, bidirectional structure. And I'm really open to changing this. The reason perhaps is why I'm using this is because they have a nice graphical language. So just quickly, what this means, I'm not going to go too much, but the idea is, optics, a morphism, optic is a morphism, and it's a bidirectional one where you go between pairs of objects, and you have a top thing that goes from, X to Y, and you have a bottom thing that goes from R to S, but they share some state in between, and you can't access that state. And there's a lot of work done by this. But the idea is I'm going to be drawing them like this, or I'm also going to be drawing them as combs, if you've seen this. And basically, whenever you see a shape like this, you're going to be thinking about optics. And there's this thing that if C, so by the way, optics are assuming C is symmetric monoidal, but if C is also Cartesian, then we can form lenses, right? And lenses have these get and put maps. And it turns out lenses are isomorphic to optics. C is Cartesian. So Cohen variable in optics is actually it's not a coincidence. I think this is the whole idea behind dependent optics and Matteo's interesting definition. There is some deep relation there, yeah.
I have another question. You just said dependent optics and Matteo's interesting definition, and I don't know about that and would like to know about that.
Oh, maybe it was actually, I don't know, was it public actually? I just said it, but
I don't think so, but
I mean, there is some interesting.
I will encourage Matteo to write this down.
Yeah. It's
actually, there's a lot of work to do to prove that his definition is the right definition.
I mentioned the key word, and people are just appearing and asking. Yes. I'm just going to go on forward and just say.
I can send him an email.
Yeah. We can talk about this later also.
Yeah.
So, but yeah, I hope that we can just work with, bidirectionality. This is going to work with dependent optics. So I'm not really focused too much. So what's an interesting idea? What's an interesting example of optics is gradient descent. And this is something that's called an optimizer in machine learning. So, it takes and I'm here again, I'm not thinking with dependent types, just simple ones. So it takes, a parameter, a change in that parameter, and it tells us how to compute a new parameter value, for instance, just by moving in a small direction, that direction of that change. And you can turn this into a lens, obviously, where the put map is the update and the get map is just the identity. And of course, we are in the category smooth. Now, interestingly enough, you might be wondering, well, are there any, is this really a lens? Why is this identity? Are there any other examples where this isn't an identity? And the answer is actually yes. So if you do other optimization algorithms, such as momentum, Adagrad, Adam, or Nestor momentum, you get lenses of this shape, where you have some internal state, S, which is being remembered. And in one of them, especially Nesterov, the get map is not identity. It's something complicated. So that's quite interesting. So optimizer algorithms are lenses. For extra work, you might notice that this has the shape of a para because it has a state here. And that's actually something I've been exploring with meta learning recently. It turns out optimizers, you can think of them as learners and learn them, but that's for future work. So is there a question, I guess, about optics before I go on the main thing, other than dependent optics? Meta learning is probably related. Yeah, it could be related to hierarchical stuff, and I'm really hoping to explore that. I'm going to actually talk a bit more about this. But until then, I'm going to now say what the main idea is. We have a symmetric model category C. We know applying optics to this gives us still a symmetric model category. And we know we can apply para to this. And we get to the main construction of today's talk, which is these generalized open learners, which is a category para optics C. And you can define them for any symmetric model category C. So it doesn't have to be Cartesian. We're also going to see it's natural in C. There's all this nice structure. But let's first unpack this definition. So objects in this category are objects of the underlying category of para, which is optics C, which in objects of optics C are pairs of objects. I'm going to write them like this, XS in these brackets in C. Now, what's a morphism between, say, XS and YR? Well, if you remember what's a morphism in para, what's a morphism in para of something? Well, we choose first an underlying parameter space. That's our object. Since we have to choose it in optics, we choose a pair of parameters. And we choose a map F, which goes from P times, now there's lots of stuff happening now. We have P times X and Q times S to YR. So there's lots of stuff happening. And we're going to now see how to think about this in a quite nice way. So what is sort of an example of an optic like this? Well, so it's an optic, and you see I've drawn something here. But if you remember the definition of an optic, we know that we choose some sort of residual M, where M lives in C. And now let's look. We have this map called L, the left map in optics, which for us, it will be of type P times X. It takes parameters, it takes inputs, and it gives us an output and some residual. And then we have a map right, which takes this utility R, the residual M, and gives us Q times S. So there's all these inputs, P, Q, S, M, R, and how to think about this. There is an easy way. So if you look at standard optics, we see that there is basically the same thing, right? We have the residual M here, but there is one added difference now. I've told you there is parameters coming from top, as I've told you that we can draw them. So we can draw P coming from top. This is the hidden input. This is the private knowledge of the agent. And we can think of time flowing downwards in a way, but also on the sideways, as it pertains to data processing. So the agent, the learner, gets an input X, it gets parameters, it computes the output Y, its prediction, or it plays a move, and it remembers some state about what it's done. Now, after receiving a utility R or a gradient, it can compute, it can send backwards the error signal or co-utility, but also you note here that it computes some sort of Q, its updated parameter, or perhaps a gradient of the whole thing. So I should just mention that the map L standing for left is here obviously on top, and map R standing for right is here on the bottom. I see lots of things in the chat. I'm just gonna go unless somebody has a question. So the whole idea is that we get automatically 2 parameter ports here. One incoming, one outgoing. The same as we have for normal inputs, now we have things going here. The most interesting thing now is that I've told you para of something is a 2 category. So we have 2 cells. And it turns a 2 cell, if you have XS, YR, and a parameterized optic F, and if I have another parameterized optic G, a 2 cell between them will be an optic as well. So now, I've been thinking about this a lot, so it is quite intuitive. But the first time you see this, it might be quite difficult to sort of wrap your mind around all these things happening and why is this important. I'm going to show you now an interesting way to think about this, which I've sort of figured out very recently. And this is how I'm internally thinking of this stuff. So I've shown you how a morphism now between XS and YR in these 2 categories is something that looks like this. It has things on the top and on the bottom. Now imagine I take this and I slightly rotate it. So I'm going to go here and just slightly rotate it like this. So you can imagine parameters flowing like this and your data flows like this. So what I'm going to do now is give you an intuition how to think about 2 cells, which are also optics. So I should give you a 2 cell and an optic somewhere else. And to do that, I'm first going to just take this diagram and just think of it maybe as a thick shape like this. It's a box, the parameters coming in, so it's inputs, it's moves out, it's utility, co-utility, and co-strategies. Yes, I think VR would be useful. So what is a 2 cell? Now remember, to get a 2 cell, we need something that goes from ZW to PQ. So we need sort of an optic. And we need to end up with a learner that should also be something of this shape that goes from Z to W. And the idea is the 2 cell for us is going to be an optic, which is a comb, which exactly fits into this. So let's see if nodability aligns this. So the idea is to reparameterize, we reparameterize from the left side, from the right side. And I'm drawing here a comb. So if comb is an optic, and this has been talked about for a while. But the idea is this is a really neat structure to think about this, because now, again, I have these pre-drawn things, which, if you just put this here, right, and forget the insides, you get a new optic, which is of this shape, right? Sorry, a new parameterized optic, which has things in, things out, and it has Z and W here. So there's lots of stuff happening, but this is how I think of this stuff. And now, after giving you all these thoughts, I'm gonna first stop for questions about this, and then tell you how this reduces to a bunch of other useful things. Okay, I'm also dying with excitement to find out what's next. So let's look quickly at the category learn from backpurpose functor. By the way, how am I doing with time? We started a bit late, so when should I aim to end?
That depends a bit on whether any of us have to leave strictly on the hour. But you should aim to finish in about 20 minutes officially.
Okay, that's great. Yeah, that should be more than fine. Okay. So let's now think about the category learn from backpurpose functor. And I've pasted here the definition, and it's in set. So a learner from A to B is a particular tuple of a bunch of these things: implementation, update, and request. Now I'm gonna show you that learn is isomorphic to para-optic when applied to set. And I'm going to do that in about 2 steps. So first of all, and I'm going to just do it basically mechanically without even telling you what this is. So we have update and request here. And maybe the rough idea is, this computes the play function, this computes the output, this computes the updated parameter, and this computes the aid that you passed to the previous learner. But we note that these 2 things have the same type except in the codomain. So we can join them together. And this is, funnily enough, what they also do in the paper. So we can write UR for what I'm calling update request. So it's P times A times B into P times A. And we also have the implementation, which goes from P times A into B. Now, we obviously see that this is a lens. This is a lens that goes from P times A, and here it's P times A. It computes an output B. And so we have P times A to B, and the map UR going from P times A times B to P times A. And we see that this is para lens of set. So this is a morphism in para lens. Is there, yeah, how is this feeling so far? Is there any questions or thoughts about all of that before I go on to the really concrete stuff? It's been really abstract so far, but now hopefully we're going to reap the benefits. All right. So I've given you a vague, sort of, well, maybe abstract, not vague, but rather precise idea of what these learners are and how we can think about reparameterizations. Now, the idea is, how do we actually construct some useful learners, some actual neural network, what it's called. And I'm going to talk about differentiation right now. And I'm going to talk about what actually, essentially what TensorFlow is doing. The framework I'm going to be thinking about is reverse derivative categories. There is other ones like tangent categories and differential and all this stuff. I'm not going to be talking about dependent types here. So this is the framework I'm choosing, and I'm hoping to extend this eventually. So a quick I'm not going to talk too much about them. What's an RDC? Category RDC, reverse differential category C, is a category which has this reverse combinator R. And that roughly means that for every morphism from A to B, you have a map a bunch of conditions. But for now, what's going to be important is that the map, this one, we think of it as the forward map. I'm seeing internet connection is unstable, but I hope you're hearing me. We're going to think of the map from A to B as the forward map, the get map of a lens, and the RF, the put map of a lens. And I'm just going to give you a quick example to see how this is something like a derivative. So first of all, the category of Euclidean spaces is a reverse differential category, and the category of Boolean circuits is as well. So if we fix, for instance, a map F on real numbers that just squares a number, then the R of F for a given point X takes a change in the output and basically gives you 2 times X times W, right? So it gives you, you can think of this as F prime times W. It gives you the change, the derivative. And how are we going to be thinking about this? Actually, for each RDC, there is a symmetric model functor that takes C into lens C. So it takes a map from A to B and just augments it with a backward pass. So it's going to give us a lens that goes from AA to BB, where the forward part does whatever the map F does, and the backward part is RF. So again, why am I telling you this? Well, oh yeah, by the way, before I go on, functoriality of this functor is the chain rule. Yeah, exactly. So it's if you think of this in vibration, this would be a particular section, yeah. So why am I telling you this? Well, actually, the action of para on symmetric monodal functors, so the action of para on the functor F from C to optic. By the way, I'm interchanging optics and lenses. So when I say lenses here, I might mean sometimes optics, and I'm really trying not to make the distinction right now. So for the action of para on this functor results in a functor that goes from para C to para optic C. This is what I mentioned in the beginning. And it's something that's called now para F. And what does this do? Well, it takes a parametrized map from A to B, parameterized by P, and gives you a parameterized optic, which has the same sort of forward map, but the backward map will be the RF, will be the derivative. So it's going to take some change and compute the change with respect to A, but also compute the change with respect to P. So this is one of the really interesting things. I'm going to talk about it also later, but for now, I'm going to give you an example. So think of and it's a really, really down-to-earth example. So let's fix our category to be smooth and our morphism to be F from R to R parameterized by R2. So it's a map of this type, which takes two weights of a neural network, takes some input, and basically does, add some bias and multiplies the weight by the input. This is one of the simplest things you could do. Now, the reverse derivative of this is going to be of type, it's going to take R2 times R, which is this. It's going to take some change in the output, and it's going to produce a change in its inputs. And it's basically just, standard calculus. It's nothing too simple, nothing too complicated. So this is how it looks. And again, I'm thinking of this in terms of information flow, remembering what it is that we're trying to do. We're going to have some data flowing in, some errors flowing out here, and some parameters flowing here. And the idea is we're going to get for any starting parameter, after we supply some data, we're going to get a change in those parameters. And I'm going to tell you how of an optics, of a parameterized optic. But before that, is there any questions about what I've said so far? All right. So I'm going to start flat out with this theorem. Gradient descent is a reparametrization of. So what do I mean by this? I've told you two things. I've told you that gradient descent is itself a lens. And I've told you that the two cells in the category of generalized open learners are lenses. So by that logic, we ought to be able to take this learner and reparameterize it by the optic of gradient descent. And I'm gonna do just that. So what I'm gonna do now is actually go up here and just luckily I can copy things, which is extremely convenient. So the idea will be that I've told you, our input was R2. Oh, this is too big. Our input was R2. Our data was some real number. We produced a prediction of a real number. We got a change, which is a real number, and we're passing back to some potential learner a change. But we compute some sort of update, so some sort of change in the parameters, which is going to be just a partial derivative of some loss. And the idea is, think of this as a comb. We can now, I'm going to just delete this. We're going to reparameterize. And just to remember, I'm going to scroll also a bit up to remember how gradient descent was defined. So we said here, gradient descent is a lens, and I'm just going to copy this so we can think about this while I. So just going to forget. So we know gradient descent is a lens whose identity is get. So we know we're going to get R2 here. We get a parameter, and we're basically sending it to the learner, but there's also something here in the blue thing, and I should perhaps just use the blue color so it's a bit more clear. So we're sending it to the learner, but this parameter is also remembered and used together with the change we got to compute. So we use the map update, which is shown here, which takes a parameter and a change. So it takes a parameter and a change and computes a new parameter value, which is going to be exactly our R2. So having our learner, we basically reparameterize it, and that's what gradient descent is. So, and this works for any optimizer you may want. So in the interest of time, I'm going to go on and just quickly tell you. So I didn't tell you how data is inputted or how loss functions work. So what I'm going to do is just quickly brush over this. And, that is, if we have a starting reverse differential category, starting parameterized map, we actually need to fix a particular loss function of type, which takes our output, some sort of notion of a true output, and computes sort of some notion of a distance. And we can assemble all of these things as follows. We use f to get a learner, which has the backwards part and also the derivative of f, of the small f of the learner. We use f to compute the, I should have named these things better, f to compute the derivative of the loss as to get an optic. And interestingly enough, we just need to supply some sort of input data. And I'm going to call this again here f of x times y. So we choose some input data, and we know that if you work out the details, the backwards wire will be ignored. On the end, there's an interesting thing. After we compute a particular loss, well, there isn't anything we do with this. And you might be tempted to have something like this, but this is not what happens. We basically send in this error signal 1 here. And here we forget things, oddly enough. Again, without going into too much detail, I'm realizing that this is something that is used in the meta learning. so you only use this if you are another learner who's using the performance of this learner as a metric. So, but that's too much for right now. The idea is that you can define parameter update for all kinds of learners uniformly, and then perform parameter update for all of them. And again, very roughly, fixing a learner, we define a parameter map as a particular update, which takes a parameter and something I've completely skipped over for now, which is, I'm going to write it here. It's called a context. And I'm going to show you in the end how that looks like. And given that context, and that context is our loss function, it's the data we put in and all that stuff. Given all that, we compute a new parameter update. And the idea is, having defined it like this, we can extend it to a list of contexts and it starts resembling something that's actually done in machine learning. Now moving on, I'm going to quickly remark on something that sort of we're working right now is, and it's this theorem from backpropagate functor, which tells us how we can assemble. I'm not expecting you to read all of this, but it basically says there's a functor from para to learn. Now, I've told you para is para of smooth and learn is para optic of set. And they're doing some interesting things here, but they're also including the notion of a cost function, and they're also including the notion of a gradient descent. So what I'm trying to do in my work is factor out all of these things into usable components that we can change as we want. So before I just give some examples, is there a question about this? Cool. So what are some examples of this? I'm going to be talking about learning on smooth and learning on Boolean circuits. The rough idea is the shape is always going to be of a learner, something like this. The red thing outside will be the context. The blue thing is the learner, and we're going to have an optimizer. Now it's stacked on top because it looks like an optic, but you can also twist it in the previous way I've shown. There's all these different ways of seeing this. This is an old picture I'm using, so it's not, but it does a good job of telling you how this works here. So standard learning of gradient descent is really allows you to pick any input space, any output space, any learner whose backwards part is different, is the derivative of the forward, any sort of, and the standard type of the utility given here is given by this particular formula, which tells you that you should take the derivative of the loss in some input. And typical machine learning just uses GD, which stands here for gradient descent. And that sort of gives you how one step of update works, and you could iterate this. Now, interestingly enough, you can think about generative adversarial networks with this framework, where now there's lots of stuff happening. You can see that we have the generator network, the discriminator network, and they're interacting in some way. The idea is that the whole GAN is a learner. So our input is either a real image or a latent vector. If it's a real image, we just pass it on. If it's a latent vector, we use the generator to produce a real image. Then we forget whether it was real or fake. And we give that to the discriminator, which then tries to predict some score. The discriminator is doing gradient descent, and the generator is doing gradient ascent. What you can also do is something called competitive gradient descent. There's a paper that figured out that all the hardships in training GANs are the fact that gradient, when you draw it like this, you might be tempted to ask, well, why are these things separate? Perhaps there should be one composite thing that uses the update for the discriminator uses the generator and vice versa. And this is exactly what competitive gradient descent does. They have a highly complex function here, which uses them in a particular way to iron out many problems with GANs. You can also do autoencoders, where you have a encoder network, which takes, say, an image, compresses it to some latent space Z, and then you have a decoder which decompresses it back. And this is usually much smaller, so you have to remember particular information. And the idea is, this also fits in the framework. Now, both of them are trained with gradient descent. What you can also do is just change this completely, and instead of learning on smooth, you can learn on Boolean circuits. There's a paper that does this, and it's called reverse derivative ascent, and it's quite an intriguing perspective, and it exactly fits in this old framework. Boole circ is a reverse differential category, and you can do all these things, and they're drawn in a slightly different way here. There's all this stuff. Actually, I was thinking of maybe talking about open games and code strategies, but I can say that if you're interested. For now, I'm going to skip this and just go to do and maybe future work. So I've just went through a lot of stuff, and there's lots of stuff to iron out and really to understand the perspective that we should be having on these things. What's interesting really is to understand other optimizers. So we know we have a description right now how these optimizers work, but really understanding the details and how it pertains to meta learning is quite interesting. Para itself, I've told you it's an entofunctor on SNC, but it's also a monad. And the idea is that the monadic structure should allow you to take a learner of learners, just as in the join of a monad, and collapse them into a learner. Right now, we're also talking about automata learning. There's interesting stuff that's happening on set, where the backward wires aren't derivatives of the forward ones. And it turns out these seem to fit, at least in our preliminary thinking in this framework. Now we're trying to think about this. There's really exciting work on open dynamical systems, which I hope to get into and see how it relates to this. One thing I also haven't talked about, and I would like to more deeply understand, is how probability distributions fit on this. Namely, para and optics are pretty general, and they assume only symmetric monoidal structure. So we ought to be able to think about probability, namely of Kleisli categorical, we should be able to think about the Kleisli category of a probability monad, which isn't Cartesian. That category isn't Cartesian, but it is monoidal. So we should be able to fit this into the framework. And the general idea is, these things are pretty general. What else can we model? There ought to be, there's nothing assumed other than we can put things in parallel and in sequence. So it would be interesting to see what else can we model. And thank you for listening. That's all I have.
Okay, generalized abstract clapping.
That was excellent. Thanks a lot.
Thanks.
Yeah, this is beautiful.
So maybe, sorry, I have to run it short to quarter past because I have to teach. I would be interested in the stuff that you actually jumped over. But I can also wait for others to just ask questions on the stuff you already did.
Well, we haven't had a talk on open games yet. So what I realized earlier is that the first 3 CyberCat seminars actually really do follow on from each other in a really nice way. So talking about open games will technically go out of order at this point.
Okay, fair enough.
But maybe everyone here knows how open games work, so maybe it's okay.
I'm fine with that. I'd also talk about it at a different time.
I did mention this to you at some point. I told you that Bruno had invented an improvement to the definition of open games.
Yeah, and I just saw it scrolled by, so that's why I was. So I can say quickly the idea, and it's exactly what I mentioned before. Open games have the idea is to think of strategies of open games as inputs. So, you've seen the usual open game. We have X to Y and R to S, and there is an optic. But the idea is we also have strategies coming in, and the idea is there ought to be something else, and that's the theorem. Every open game can be factored using co-strategies, and it seems to be solid. Namely, you can think of an open game as practically a para-optic of something on the base category, whatever you want, plus a particular selection function. So open game is basically para-optic C plus a selection function, which goes from sigma. So it takes, a particular update and tells you how, gives you sort of an equilibrium. So it does that for every sort of morphism. You have to be careful. But the idea is to introduce the notion of a co-strategy for an open game. And basically, yeah, it's quite unworked and there's lots of stuff to think about, but it simplifies. I'm using it to think about open games right now.
Right, so you can canonically take sigma prime equals R.
Yeah.
But you get more flexibility if you allow sigma prime to be other things.
Yeah, and the way to think about this is sigma prime gives you sort of the intrinsic utility of the agent. The agent doesn't just propagate back co-utility, something that previous players should use, but it computes something for itself. If you think about it in the terms of bookies, in the original open games paper, when you give somebody a champagne, he buys it for you. The intrinsic utility actually would tell you that the person actually takes a bit of a slice of the money for himself. And he doesn't have to, but it tells you how that person has some intrinsic utility of their own.
I see. Okay. That's interesting.
So I'm basically sold that this is the right way to do it.
Okay.
It's a refinement of the standard definition of open games. So this gives you strictly more data.
Yeah.
And it's just so pretty. And it includes what we normally do as a large special case.
Yeah. Yeah, I think I'm also intrigued by it because the problem with the strategies in the framework as we have it now is basically it's all hidden. It's hidden from plain sight, and it's kind of ugly a bit because normally this is at the forefront of what we talk about in terms of game theory.
Yeah, that's true.
Yeah. Like the way I think about it, each agent, we always say, well, this agent is trying to do something, and sigma prime allows you to say, hey, this is the type that the agent is optimizing in a way.
Yeah, it makes the individual optimization target explicit.
Yeah. Yes. Okay. Have you thought about? There are classes of games like coordination, so special cases of the general class. What this would correspond to?
Actually, I don't know much about those. Yeah.
Okay. I'm just mentioning this because these games typically have a specific shape already in open games.
Yeah, you could do the same thing. So if you had a symmetric, like a coordination game, for example, you could take sigma prime to be just R.
Yeah.
Whereas for a general by matrix game, it would be R squared.
Yes. Okay. Okay, that's interesting, because that's also interesting because it would allow to differentiate more between different kinds of games and kind of represent more structure that is normally completely out of sight.
Yeah.
Okay, thanks. That's good.
And it fits for free into Bayesian open games, for example, because it's just done generically.
Yes, makes sense.
Toby had a raised hand, still does have a raised hand.
Yeah, I don't have much time to chat, so I guess I would like to have a catch-up meeting with you, Bruno, at some point and talk about this in more detail. Because I feel like that possibly also including this generalized open game co-strategy definitions feels like it should connect up a bit with what I was trying to do with active inference, where you have a sort of dynamical system. I don't know.
Yeah,
I don't really have time.
Like you might be able to have a nice chat and sort of.
Yeah, and as I said at the
yeah.
And I was saying at the beginning that this like this meta learning stuff you're talking about feels like it fits into this thing I've been thinking about, where you have systems which have subsystems which are trying to learn, but they're trying to learn based on information from the bigger system. But again, I don't really have time to talk about that. I just wanted to ask one quick question, which is, you talk about gradient descent, but most actual machine learning, it seems to me, uses stochastic gradient descent. Have you looked at that?
So stochastic gradient descent pertains to the idea that if we have, say, this is one step now of learning, and I didn't really tell you. So this is the input, this is data, but it pertains to sampling a particular point of data at different times. So if we stack things like this, the things coming in right now would be different than things coming in. So the randomness arises from that. So it still is gradient descent, but the stochastic pertains to the fact how we sample data. So I would say, adding the actual data input output and making it clear in a probabilistic setting of the stochasticity, I didn't really think about, and that's something I'd like to do.
Yeah, as I say, I'd like to chat about the sort of probabilistic settings. I feel like it should connect up. But yeah, I've got to head off. So thanks so much, Bruno.
Yeah, thank you. Bye-bye.
Toby, you're talking in 2 weeks, right?
Yeah, I think so. I need to figure out what I'm talking about, but I'll decide that next week, probably.
Okay. Do we have more questions? Do I have a question? I don't think so. I just think this stuff is incredible. My question is, why the heck have you still not written a paper about this? Except, no, I know you're writing a paper in progress.
I was actually just about to ask the same. Where can we actually read this?
I mean, yeah, it's honestly, while I was just doing this presentation, a lot of things cleared up for me the way I should present it. So
you're allowing the perfect to be the enemy of the good. You're also allowing Strathclyde people to pull you in too many directions.
Yeah, I mean, it's moving along slowly but safely. So hopefully soon.
And a paper that followed the structure of this talk would be a super nice paper.
Yeah. May I ask you, maybe this is completely naive or stupid, but if you go to the adversarial representation of what you had, I think it was more down, the last thing. Yeah, sorry, up. Yes, exactly. Yeah. This kind of stuff. It seems to me, I mean, just looking at this, there seems to be kind of more emphasis on the sequential mapping of these components in the blue thing. Are there also things which are more parallel or have combinations of sequential and parallel kind of combinations? Maybe this doesn't make sense at all, but here, I mean, from the way I think about it as an open games terms is there is a first mover and a second mover. But is there something corresponding to parallel or partial parallel? That one is moving first and then there are several moving second?
So that's an interesting question. Like when you now say is there parallel things, I'm like, oh God, that should be a simple question to answer. I don't know. I think that comes up to my mind is recurrent neural networks, where you can think of it as, as a step at each step. So there's a number of steps, and each step to compute an output depends on the previous player, quote unquote, doing something. So that's one way to do it. But actual things like you mentioned, I'd have to think about it, I guess. Yeah.
Okay. And sorry, can you say something? I missed it on this. The next point, this competitive, I think, whatever it stands for, competitive.
Yeah,
blah,
so
blah, blah.
it's called competitive gradient descent, and it's a particular update rule introduced recently for generative adversarial networks that sort of takes. So if you look at the standard gradient descent, each the generator and the discriminator update themselves without thinking about what the other person is doing. So
Yes.
the same way, if you think about the Nash equilibrium or something, the same way where you should sort of consider what the other person ought to be doing and sort of some higher order thinking, competitive gradient descent does something in that vein. And I can just put out some sort of keyword instead of, if you have two linear function, this update, I think they're using the word bilinear. So in a way you could do quadratic optimization where it's like doing like Newton's method, but they're doing something in between where it's bilinear, where you have two different things, and the updates that the discriminator will do will actually also depend on where the generator is at. And the update that the generator is doing will depend in a really, and if you look at the paper, there's lots of equations, and I haven't worked that out, but there's lots of the ideas that, thinking about what the other person will doing will stabilize the whole training, and they've shown some incredible results pertaining to this.
I see. Okay, maybe this could be completely off, but there seems to be kind of a natural ordering in complexity from top to bottom, in the sense of what is happening in this pink or whatever you call this color boxes. A natural question would also be, can you generalize this to make this a game itself? And the reason I'm asking this is from a specific perspective, actually. There is something in the auction literature which is called automated mechanism design, where the idea is that you have some underlying players that are playing a game, and then you have a kind of another player optimizing a mechanism that these players actually have to play.
Oh, you mean like meta optimization?
Yes. And in some sense, there would be, what I'm thinking about is actually there would be another box on top. So you would have another player inside of that, which is the designer, and then the designer is learning something, basically. And the learned object is actually the mechanism that he's applying, the auction format, for instance, that is played.
So that's what I meant by meta learning.
I see.
So I have a particular paper in mind. It's called, interestingly enough, Learning to Learn by Gradient Descent by Gradient Descent. So what it does is something along the lines of what you said.
Okay. Was it already accepted?
Sorry?
Sorry. I just said, was it already accepted?
I mean, yeah, it's like 4 or 5 years old, maybe, the paper, something like this, maybe less. I don't know. Well, but basically the idea is, I've told you, that you have an optimizer in a particular lens.
Yeah.
But it turns out you can actually learn the optimizer. So you can have, the idea is to,
I'm afraid
I can tell you roughly, very, very roughly, is that when you do this training, when you do it for a number of steps, when you, if I duplicate this and you imagine this time flowing on this side, right?
Yeah.
It turns out that this looks exactly like a recurrent neural network, where now you can actually learn, and you're going to have some other inputs and outputs, and you're going to learn how to do the blue thing, which is going to be the gradient descent. So instead of doing the update, which takes the change in parameter and the previous parameter to produce a new one, you're going to have another input that tells you how to do this, and you're going to unroll in another dimension, which obviously I'm not going to draw here. Basically, I've been thinking about this. I don't know whether that's what you meant, but there is a lot of work being done on that front in machine learning.
Yeah. Okay, that makes sense. So I think, okay, that makes sense. I think that's enough for me to think about, actually.
Yeah, we could talk about this also offline, and I'm interested in expanding and thinking about this stuff.
Yeah, I'm very much interested in I'm interested in that, and also if you have written something up that maybe would be even more interested in reading it, actually. It's really nice.
Thank you.
Sorry for hijacking this a bit, but I have to run off because I have to teach now. Let's talk soon at another point in time about this, and keep me in the loop if you have something written up.
I'm just going to shout the word reinforcement learning.
Yeah.
Yes, I'm convinced that reinforcement learning is a massive expansion of all of this as well. It just fits together.
Okay, thanks. Nice talk.
Right.
I have to leave. See you soon.
Yeah. So reinforcement learning should be replace your loss function with something that's not a function. Replace it with a very complicated object representing the environment, potentially containing other agents who are also doing learning by gradient descent.
Well, that's essentially the core argument, or one of the core arguments of our co-author paper. So.
But
Sorry, I didn't quite catch. What did you say, Jerry?
So that the paper that Jules and I and a bunch of other people at Nascent are working on, essentially the idea of doing away with a loss function and replacing it with something arbitrarily white box is one of the core ideas.
right, that's not quite the same because reinforcement learning is still numerical. It's just that the thing that gives you the loss has an internal state of its own and is potentially very complicated. I don't want to, Bruno, don't think about this too much because it doesn't belong in this paper.
No, I'm just interested because it's quite related to this perspective that you can think of GANs, that this discriminator as a sort of a loss function which you learn, and there's all this unexplored stuff on that front as well.
Yeah, this is a big part of why I want to get you and Philip and me in the same place at some point soon.
I mean, all interesting loss functions are non-stationary, right? It's if you can prescribe the problem in advance, then it's probably not a terribly real world problem.
Yeah.
Anyway, that was a thoroughly enjoyable and illuminating talk, Bruno, so thank you very much indeed.